Imagine you have a scatter of data points and you want to find the line that fits them best. You could guess the slope and intercept, measure how wrong you are, adjust, and guess again. But with millions of possible lines, how do you find the best one efficiently? Turn it into a geometry problem. Define a cost function, a single number measuring how wrong your current parameters are. Plot this cost against all possible parameter values, and you get a bowl-shaped surface. Finding the best parameters is the same as finding the bottom of that bowl. That is the problem gradient descent solves. Let's start simple, with just one parameter. Picture a smooth curve. The cost as a function of theta. You're a glowing dot sitting somewhere on this curve, not at the bottom, but you want to get there. The derivative at your position tells you the slope, which way is uphill and which way is down. If the slope is positive, you're on an uphill ramp going right. Step left. If negative, step right. In both cases, stepping opposite to the slope moves you downhill. This gives us the update rule. New theta equals old theta minus a small number alpha times the derivative. Subtract the slope, take a step, repeat. Watch it work. The dot senses the slope, nudges downhill, and does it again and again. Near the bottom, the curve flattens, the derivative shrinks, and the steps naturally get smaller. The algorithm gently halts right at the minimum. This is convergence. How big should each step be? That's controlled by alpha, the learning rate. Think of it as the size of your boots. With tiny boots, you tiptoe safely but excruciatingly slowly. With well-sized boots, you stride elegantly to the minimum in a handful of steps. But with boots that are far too large, disaster. Your giant leap overshoots the minimum, landing higher on the other side. The next leap overshoots again, even further. Instead of descending, you diverge. The learning rate is a hyperparameter, not learned automatically, and choosing it wisely is critical. Now let's go to two parameters. Two parameters create a surface in 3D space, see, a landscape with valleys and ridges. Our dot now sits on this surface, and the single derivative becomes a gradient, a vector of partial derivatives, one for each parameter. Together, they form an arrow pointing in the direction of steepest ascent. To go downhill, negate the gradient. The update rule stays the same in spirit. New theta vector equals old theta vector minus alpha times the gradient. Step in the direction of steepest descent and repeat. The elegant symmetry is that this identical recipe works in any number of dimensions. Looking from above gives us a contour map, like a topographic map of the lost landscape. The rings are lines of equal cost. The gradient at any point is perpendicular to these rings, pointing outward toward higher cost, so the negative gradient points inward, toward the minimum. On a circular bowl, the descent path goes straight to the center. But on a stretched elliptical bowl, what mathematicians call ill-conditioned, the gradient doesn't aim straight at the minimum. The path zigzags inefficiently back and forth across the narrow valley. This zigzagging is exactly why researchers build more advanced optimizers, like Atom. Real neural networks have millions or even billions of parameters. We can't visualize that space. But the math doesn't care. The gradient is still just a vector of partial derivatives, now with a billion entries. And the update rule is identical. Same formula, unimaginably larger space. This is the engine of modern AI. One practical challenge. Computing the exact gradient means summing over every data point in your training set. With millions of examples, each step is expensive. The solution is stochastic gradient descent, or SGD. Randomly grab a small mini-batch of data points and compute an approximate gradient from just those. Think of estimating the average height of people in a city. You don't measure everyone. A random sample gives a good enough estimate. SGD does the same with gradients. It's noisier, but dramatically faster per step, and converges well. The noise even has a hidden benefit. It helps the algorithm escape shallow traps, which brings us to gradient descent's most famous pitfall, local minima. The algorithm is greedy. It only sees the slope right where it stands, not the whole landscape. It can fall into a shallow dip and get stuck, never knowing a deeper valley exists elsewhere. Closely related are saddle points, where the gradient is 0, but it's a minimum in one direction and a maximum in another. In high-dimensional spaces, saddle points are actually more common than true local minima. Fortunately, the stochastic noise in SGD helps the algorithm jitter-free and keep descending. In practice, gradient descent finds solutions that work remarkably well. Let's bring it all together. Gradient descent is a simple loop. Start at a random point, compute the gradient, step opposite to it scaled by the learning rate, and repeat until convergence. That's it. 4 steps, the entire foundation of modern optimization. Watch it close the circle. Back to our scatter plot. Gradient descent takes the random line, computes the gradient of the mean squared error, nudges the slope and intercept, checks again, nudges again, and within moments, the line snaps into perfect fit. The dot on the lost surface spirals elegantly to the bottom of the bowl. This one idea, compute the gradient, step opposite, is the foundation of linear regression, deep neural networks, image recognition, language models, and drug discovery. The deepest insight isn't mathematical. You don't need to see the whole landscape. You just need to know which way is downhill, right where you stand, and take one small step. Repeated thousands of times, that act of walking downhill is enough to teach a machine to see, to speak, and to reason.